Before we start with the Java 8 specific features right away, let's first make sure this course is for you. In order to be able to follow along, you'll have to be familiar with using IDEs and basic Java. If you're not familiar with basic Java yet, these course titles can really help you fix this. Learning Java, Java 11 Essential Training, and Java Essential Training for Students. If you're not familiar with Java, it would be good to first take one of these and then come back here so you can dive into the Java 8 features with me. If you have the Java basics down already, let's get started. Most Java developers didn't really like dates. Working with dates and times, that is. But this all changed since Java 8. Before Java 8, dates were taken care of by the Java util date and Java util calendar. Now, dates are arranged with the Java time package. It's thread safe to use. This means that it can be used in a concurrent environment. And as a bonus, it's easy to work with. This is really a walk in the park compared to the old ways of dealing with dates. And there's even logic for time zones included. So, how do you know whether something you're working with is part of the Java 8 and later dates? Well, simple. It comes from the Java time package. The specifics of this Java time package are rather well documented by Oracle. As you can see here, there's a lot in the package. Let's for now first focus on 3 of them. First of all, local date, which is the type used for storing a simple date. Also, local time, which, you may guess it, is the type for storing a simple time such as 8:04. And let me blow your mind, local date time. This is for when you want to store a date and a time. Alright, let's have a look at these local dates, local times and local date times in IntelliJ. So I'm first going to be creating a main method. And in this main method, I'm going to start with creating a local date. So you need to import the java.time local date to do this. And I'm going to call this local date LD1 and I'm going to assign it the value of right now. There we go. And I can also go ahead and create a new local date here. But this time I don't want to assign now to it. I'm actually going to build this local date. And I'm going to say local date of, and then I need to specify a few things here. So I'm going to choose for 2014, the 3rd month, and the 17th day here. So please mind that in here the 3rd month really means March. So we're not starting to count from 0 anymore, which is definitely an improvement because we refer to March as a 3rd month and not as the 2nd month. But do be aware though, because if you come from before Java 8, this might be shocking. Alright, and let's go ahead and create yet another local date. But this time, instead of going to create with the number of the month, I'm going to use the enum. So I'm going to say local date of, and then again, let's just go ahead and pick 2022, go for December, and let's pick December 25. There we go. I can now go ahead and print these. So let's just go ahead and print all of them. I'm going to do so on separate lines. There we go. And as you can see, it has created our dates. So let me show you what happens when we enter an invalid date. So I can go ahead and create an invalid date over here. So what do I mean with an invalid date? Well, let's just go ahead and call it invalid date, just to be very sure that you understand that this is not going to be working. So let's just go ahead and create something simple like the 13th month and then just the 1st or something like this. So as you can see, this is compiling fine. But if I'm going to run this, we'll get a nice exception. As you can see here, we get a date time exception, with a very helpful message. It says invalid value for month of year, and then it also specifies the valid values for us 1 to 12. That's it. So be aware that when you work with dates, they don't crash until runtime. Okay, let's have a look at local times. So this is actually similar. Instead of local date, I'm going to say local time here. And again, I can be creating the local time using local time now. And again, I will be importing this because otherwise it won't find it. So let's go ahead and create another time, which can be done in a similar way of creating the local date. So let me show you local time dot off. And then in here, I just need to specify the hour and minute. So let's just go ahead and say it's 10:05. And as you can see, IntelliJ is also suggesting seconds and nanoseconds, but I think this is too specific. I'm just going to leave it at this. And now I'm going to be printing both again. And as you can see, it's printing 2 times now as well. It's 11:14 and it's printing our custom-made time 10:05. Alright, let's make this slightly more complicated. We're going to be creating a value for date and a time. And this is called a local date time. And again, we can go ahead and create a local date time using the now method, after importing it, of course. But I can also go ahead and create a local date time by entering all the values myself manually. So let's do that next. Local date time off. And then we start with the year, then we specify the month and the day, and then we need to specify the time. So let's just go ahead and go for 2:03. So this is one way to do it. Again, we could also be entering seconds and nanoseconds, but I don't want to be so specific. Let me show you the last way to create a local date time. And this is actually by reusing our previous objects, the local dates and local times. So I can create a local date time using a local date and a local time. So let's just go ahead and use local date 1 and local time 1. And now I can go ahead and print all of these again. And let's run it and see what's going to happen. And as you can see, this time it has created them all. So first we have the 3 local dates, then 2 local times, and we end with 3 local date times. You may wonder, why are the first local date time and the last local date time the same? Well, that's because my computer is quite fast, and determining local date time now was just as fast as determining local date and local time before. As we just saw in the documentation, there are a lot of classes in the Java time package. Some of them deserve some extra explanation. The month day, which represents a combination of a month and a day of said month. The year month, which is a combination of a year and a month. And the year, an object representing a certain year. Let's move over to IntelliJ and have a quick look. Let's look at the month day. And we can go ahead here and create a month day. I again have to specify the month and then just go ahead and specify a day. So there are some nice methods right now. So for example, I can go ahead to say month day, and then I can turn this into a local date using the add year method. So I can say I want to have this at 2022. And I can actually store this as local date, since this is returning a local date. There we go. Something similar can be done with the year month. I can go ahead and create a new year month. And I'm going to use the now method for this. And then on this year month, I can actually go ahead and say an add day. And then when I enter the day, I can go ahead and create a local date yet again. So I'm going to be storing this in a local date. There we go. In the next video, we're going to have a look at zone datetime and zone ID. So let's add some zones to our mix. We have just seen how we can create local datetimes. Will these work to create appointments? To some extent, probably yes. But say that we would like to set a meeting, chances are that we're in different time zones. And in order to get the moment right, we'd have to write a different local date time in our calendar. Don't zone out now, because this is where these zones come in. Zones are going to help us capture an actual moment. There's a special object for this in Java, the zoned datetime. At this point, the word local datetime might make more sense. It's only meaningful locally. It's the local date and time. In order to create a zoned datetime, we'll need a zone ID. A zone ID represents a certain time zone. There are many zone IDs. Let me show you. Let's go ahead and see all the zone IDs that we're having. So I'm going to be creating a for each loop here, and I'm going to be running over strings, and I'm going to get them from zone ID, for which I'll have to import java.time.zoneid. Then I'm just going to say get available zone IDs. And these might actually be different for your system, so mine might look different. So I'm going to go ahead here and print the zone ID. And as you can see by the tiny scroll bar on the very right of my screen, there are a lot of zone IDs over here. And with these zone IDs, we can actually do more. So right now I just have the string representation, but what I could also do is go ahead and say I want to create a zone ID object. Say I'm going to call it zone ID. And then I can create it using the zone ID of. And then in here, I can just go ahead and use our zone ID. So we can use the name to create the zone ID with the static of method. Then in here, instead of going to be printing the zone IDs like I just did, I'm going to be using the zone ID1 dot get display name. And then actually I have to specify a certain text style here, and I'm just going to go ahead for text style full. And then I also have to add the local, and in this case I'm going to be choosing the one for the US. Let's go ahead and catch this in a string. And right now I actually want to be printing both of them. So I'm going to say print the zone ID, and also make sure to go ahead and print the zone ID display name. Let's run this and see the difference. And as you can see, for example, America Los Angeles translates to Pacific time, and Europe Monaco translates to Central European time. Alright, so we know how to create zone IDs. Let's just go ahead and grab one. I'm going to choose US Pacific. And what I'm going to do next, I'm going to create a zoned datetime. So this part over here, I'm just going to comment it out. Alright, let's create some zone datetimes. First of all, we'll need the zone ID. There we go. And there are actually multiple ways to create a zone datetime. Let's start with creating one using the local datetime. So I'm going to be creating a local datetime, again called LET, and I'm just going to grab the current time for this. Now, if I want to create a zoned datetime, and I do, I actually have to import it, and I need to go ahead and say ZDT1. I'm going to be creating more zone datetime dot off. And then, as you can see here, as the first argument, I can provide a local date time, but I could also go ahead and provide a local date, a local time, and then a zone ID. But I'm going to choose for this first option, and I have to specify the zone ID. Now I can go ahead and print my ZDT1. And as you can see, it has printed a zoned datetime right now. In the output, it specifies -7 hours and US Pacific. Alright, but we can do even more. We could also create a zone datetime like this. I can now go ahead and grab our LDT and say add zone and then provide the zone ID. This is yet another way of creating a zone datetime. Of course, I can also go ahead and create a zone datetime using the zone datetime now method. You may wonder which time zone is going to use. Well, it's going to be using the time zone of my computer. Let me show you. And as you can see, as I'm based in the Netherlands, it says Europe, Amsterdam as a time zone. Alright, that's it about time zones for now. Do you happen to know what time it is? Let's have a look at the clock in the next video. Alright, it's time to talk about the clock. Well, all jokes aside, the clock was added in Java 8 to make our developer life easier. What is the clock, you may wonder? It gives access to instant date and time using a time zone. It is a provider of the time, so to say. This is actually great for testing because you can stop a clock with this and enforce a certain time. This way, it allows for alternate clocks. You cannot instantiate it because it's an abstract class. So, if it's abstract, how to get a clock, you may wonder? There are a few factory methods to get one. Let's go ahead and get some clocks and use them to get instants. We are creating clocks so that we can later be testing our application. This way, we can test whether our application is going to be working with different times. So, how to create a clock? There's quite some ways, there's quite some factory methods. But let's just go ahead and use one that is very common. So, I can go ahead and say clock system default zone. And this is going to be returning a clock using our system's default zone. But I would have to catch this clock if I want to do something with this and store this in a variable like this. And now I can go ahead and print this clock. And as you'll see, we have created a system clock with the time zone Europe, Amsterdam. So let's see what the current time is. I'm going to use the clock to get the instant. But I do need to import the instant, and again, it's coming from the Java time package. And now if I print the instant, you'll see the current time over here. But there's more factory methods to create a clock. For example, we could also be creating one that says clock.systemUTC. And this one is going to be returning a clock which is representing the instant of the UTC time zone. So let's just go ahead and say clock1.instant and go ahead and print this right away. As you can see, it's printing the instant in UTC time. There's a lot more ways to grab a clock, but I think what's more interesting for now is to go ahead and show yet something else we can do. So we can also create a clock using another clock, but just changing the time a bit. So say we're going to be creating a new clock. This is going to be clock 2. And then we're going to say clock.offset. Then we'll have to insert a certain base clock. Let's just go for clock and then specify a certain number of hours. So I'm going to say duration of hours, and then let's just go for 10 because that's easy to calculate with. And now I'm going to be printing the time of our clock 2. And as you can see, it's working well. Or 10 at night is changing to almost 8 in the morning, which is 10 hours. There's some more things you can be doing with the clock class, but for now I think you've seen the most important ones. And you probably understand the basics of the clock class as well. In the next video, have a look at comparing dates. Did I tell you how happy we should be with this Java time package and how hard life was before Java 8? I probably did, so let me not repeat that point, but just show you how elegantly we can compare two dates in Java. There are some very useful methods available. The compare to, that can be used to compare the Java time object to another one. The is after, is before, and is equal. You may be able to guess what they're doing. We can call them on an instance and compare them to another date or time, or local date time for that matter. Let's see them in action. So I have two local date times here. One is based on now, and the other one is based on February 1st this year, 3 minutes past 2. Well, clearly that date is before now, but let's see if Java can tell us this as well. So first of all, let's just go ahead and have a look at the compare to. If I say LDT1 compare to and then LDT2, let's go ahead and see what this is going to be printing. It's printing 5. Let's go ahead and dive into the compare to method and see how that's working. Well, compare to always is giving back an int, and it can actually be used to sort our dates and times. If it's returning a positive number, then the instance on which the compare to was called was bigger. If it's returning a negative number, it was smaller, and when it returns 0, it was equal. We can see the logic over here. So what it first tries to do, it first tries to see the local dates. And then it's actually going to be comparing them. If the result is 0, then it's going to go back and it's going to compare the local times. If that comes back at 0, it's going to be comparing the details. Alright, let's have a look at the other methods. So we can also say LDT1 is after LDT2. So I'm just going to be printing this like this, and we can see this all at once because it's actually very intuitive. And I also want to do is before and is equals. Is equal. And change these. And as you can see, these last three return booleans. It's after, that's true. It's not before, and it's not equal. Alright, we have seen that when we print the local dates, or the times, or the local date times, etc., the formatting is very off. In the next video, we're going to have a look at this formatting. What happens if we print the datetime? Well, the toString method is called, and this is what it looks like. Chances are you'll need a different format. The good news is that's possible. We can do so using the Java Time Format package. It contains a datetime formatter, and we can use this for parsing and printing date and time objects. It has a lot of predefined formats in it. Let's move over to IntelliJ and have a look. Alright, so here we have a local datetime, LDT, and I'm going to format this one. I'm going to store the result in a string formatted date. I'm going to use the datetime formatter for this and make sure that it's imported. I'm importing it on line 4 with java.time.format.datetime formatter. So alright, on this datetime formatter, I'm going to use one of the presets. I'm going to choose one now first that we have seen already, and that's the ISO local datetime. And then I'm going to call the method format and insert our object LDT. Then I'm going to be printing our formatted date. And as you can see, it looks the same as our default date. Well, that's not very useful, is it? So let's now go ahead and change our ISO local date to basic ISO date. And you'll see that this actually looks very different. So I'm going to go ahead and run it again. And now you will see that it's printing the year with the month and the day concatenated. There are many other predefined formats. Just play around and find the one that you'll need. So, what's your favorite type of date? Well, datetime format it is. Great news, it doesn't matter to Java. You can create your own datetime patterns too. In order to do so, we'll need to create a pattern. This pattern consists of all sorts of letters. They have a special meaning, as you can see in this table. For example, lowercase m is for minute and uppercase M is for month. When you have one uppercase M, this means you're getting 1 digit. 2 uppercase M's means you get 2 digits. 3 uppercase M's means you get like a short name like Feb. And 4 uppercase M's means that you get something like February, all spelled out. Using these letters, we can create patterns using the of pattern method on the datetime formatter to obtain a datetime formatter. So let's have a look at how to do that. Let's go ahead and create a custom datetime formatter. And we're going to do so using the of pattern method. And in here, I'm going to specify a string using these special letters. So, for example, I could say I first want a day, then I want a month all spelled out, and then I want a year all spelled out. And then we can go ahead and use this datetime formatter to format our dates. So again, we're going to be formatting LDT here. And as you can see, it has now spelled out our date. It says 08, the day, July, the whole month spelled out, and 2022. There's actually one other typical way to format your dates, and that's using the format style enum. We could do so in a way like this. So again, I would be using the datetime formatter. And this time I'm going to use the of localized datetime. And then in there I can specify the format style. For example, I could go for medium. And then in there I would say format and then go ahead and format our LDT again. I'm going to catch the result in a string. And then let's now go ahead and print a string as well. And we'll be able to see the result. There we have it. This is the medium built-in format style. There's actually a lot of more options for this, but these are the basics. And you'll definitely explore them when you go play around with the dates and times and format this more. In the next video, we're going to have a look at period. what if we needed to know the time between two dates in Java? We could use the period class to work with this. The period class represents an amount of time in days, months, and years. With period, we can get a, period bigger than a day. Let's move over to IntelliJ and have a good look at periods. So in here I have created the class periods. Actually, I do this a lot, and this is that I'm using a plural as my class name, which is typically a bad practice. But in this case, if we would go for period, I'd probably have to call it period example or something, else it would interfere with the actual period that we're working with. So, how to get to period? Well, there's, again, multiple ways to do this. But let's start with the period of method. And as you can see here, we can specify certain things. So we can go ahead and say 1 year, 1 month, and 1 day. And now we can go ahead and print our periods. Well, that is, if we call it in a variable. There we go. So let me show you what this looks like. And as you can see, it's printing P, 1Y, 1M, 1D, meaning it's a period of 1 year, 1 month, and 1 day. We can also specify a period consisting only of days. So I can go ahead and say P2 equals period of days, and then I could say it's 100 days. And now if I were to print this, it's going to leave out the year and the month. Let me show you this. As you can see, now it just says P100 and then it says D. There's yet another way to get a period. What we can also do is we can have two local dates. So let me just go ahead and create two local dates here. Local date 1, importing local date of course. And then I'm going to say local date of. And then we're going to specify this year, the first month and the first day. All right. And then I'm going to say local date LD2. And then I'm going to use now for this. And then we can create a period saying period P3 equals periods. And now we're going to use the between methods. And then we're going to specify a start, which was LD1. And then we're going to specify the end, LD2. And then let's go ahead and print this as well. And as you can see, it specifies a period of 6 months and 7 days. But you may wonder, what if we want to have this in days? Well, there's one thing that you cannot do in order to do this, and that's to use the getDays methods. It's tempting because you may think, well, getDays is probably going to print this for me in days. What this is really doing is just getting the day part, which in this case is 7. So how to get the number of days? Well, it's actually in a different package, but let me just show you to be complete here. So what I would do, I would say long number of days between, well, let's just go the dates here, super long variable name, but very descriptive. And then I would use the chrono unit. And then I can specify the days as the unit, and then I can work with between. And in here, I can actually send in LD1 and LD2. And then I can print the number of days in here. So let me show you that as well. And as you can see, it says 188. Well, if you don't believe it, go and calculate it yourselves. But this looks about right to me. What if we needed an amount of time smaller than a day? We'd be working with the duration class. That's exactly what we're going to explore in the next video. Local dates, local times, local date times, and zone date times are immutable. This means that the value of the object cannot be altered after the creation of the object. So technically, you cannot alter them, but we can definitely do calculations with them. The result will be a new object with the new values representing the new date and or time. I know it almost sounds like I'm selling it, but it really is my own not sponsored opinion. There are beautiful methods out there for doing calculations with the dates and the times. They're captured by very many plus and minus methods. We use duration and periods to add or subtract to or from a date or time. And then we also have the with and with something something methods. These return a copy of the object with the specified attribute altered. Let's move over to IntelliJ and have a look. So let's go ahead and alter some dates. In order to do so, we'll first need some dates. I'm just going to be working with a local date time here. And I'm going to create one again using the now method. And then in here, I want to show you that I can actually go ahead and alter our date time. But if I were to alter my date time, it would actually not be altered. It's just returning a new object with the specified properties that come out of the calculation. So I can go ahead and say LDT1, and then I can, for example, say plus days, and then say 7. So right now, it's the 8th of the month, so it should be the 15th after this. Let me show you. And as you can see in the output, it says 2022, July, and then the 15th, because we added 7 days to ours. Alright, so as you can see, it's 8 to 12 right now. So what would happen if you were to add 8 minutes? Well, actually, exactly what you would expect. It will also just skip and continue with the next day. So I'm going to change this. And as you'll see, it will also alter the day. So this is actually doing a proper calculation. It's not just updating the minutes. So we also have minus methods, and they're very intuitive. They do the exact same thing as the plus, but then the opposite. More interesting for now is to have a look at the with methods. So I can go ahead and create a new local date time, say LDT3. And then in there, I can be using LDT1. And this time I can say with, and then specify maybe a specific month. So say that date, but then with the 9th month. So if we're going to be printing this now, we'll see the same date, but with September instead of July. And as you can see, it's still the 8th of July right now. So if we just change the month, it's going to change into September. Alright, I also promised you that I would show you where duration and period would come into place here. Well, we can actually also use plus and minus for working with durations. So in here, I can say local date time, and I'm going to call this LDT2A, and I'm going to say LDT1 plus. And then in here, I can just go ahead and create periods of, and then let's just now go ahead and say weeks 1. Import the periods. There we go. Next up, let's print this and see what will happen. And as you can see, in the second print statement, we have been adding a week to our local date 1, resulting in the 15th. Well, let me show you how to subtract something. It's very, very similar, but I also want to show you very briefly how we can do something similar with duration. So I'm going to use LDT1 again, and then I'll say minus this time. And now we're going to be creating a duration, and I'm going to do so with off hours, and I'm going to be subtracting 12 hours here. And then let me print this. Actually, it might start to become a bit vague, so let me print this to be a bit more clear like this. There we go. And as you can see, we now also have one with the alter time, where the time is minus 12. So this is how we can easily calculate with local local times, local date times, and also zone date times. We can either use the plus and minus methods and then just go for the very specific ones where we'll be simply adding minutes, but we can also go ahead and use the plus and minus one where we can add and subtract period and duration. Alternatively, we can also use the with methods. We can use these to alternate components of the dates. And I know I've said this already a few times, but dates are immutable. So please be aware that if we add to LDT1, so on line 12 we're saying LDT1 plus minutes. This is not altering our LDT1 object at all. This is staying the exact same. The only thing that's being done is that there's a new object returned with the specified value. Next up, we're going to have a look at how we can convert old dates and calendars to objects of our Java time package. The duration class is used to work with amounts of times that are expressed in nanoseconds to days. Minutes and hours and the days unit can be used to work with durations. Let's see how to obtain a duration. Alright, just as with the method, we can create a duration using the duration of method. And then we have to specify a certain amount followed by the temporal unit that we'd like to use. So let's go ahead and create a duration of a day. So I'm going to say amount is 1 using the chrono unit days here. And then if we go ahead and print this, you can see our duration of 1 day. In the print statement, you can see that it says PT 24 hours. So it has translated our day to 24 hours. We could also have chosen a different chrono unit. For example, minutes, seconds, etc. What we could not have done is creating a bigger one. So we could not have said months, for example. And then if I were to run this, you'll see that it would actually crash because we're using a chrono unit that's not supported. Alright, so let's change this back to days here. There are actually some different ways in which we can create a duration. We can go ahead and create a duration using one of the more specific methods. So we can say duration d2 equals, then duration, and we can, for example, say of hours. And then we only need to specify the number of hours. If I'm going to be showing this, you'll see that it says duration of 5 hours. So let me show you. There you have it, PT5H. Well, let me show you one more way to get a duration. And it's actually similar to one that we have already seen. It's the between method. So this time I'm going to be creating 2 local times, importing Java time, local time, of course. And then I'll say local time now. And I'm going to be calculating the difference between, well, what shall we do? Let's say 3 in the afternoon. So go ahead, say 15,0. And then I'll be using a special method, the duration between here. And then we specify LT1 and LT2. And then I'm going to go ahead and print this duration as well. And as you can see, this is printing something very specific. It says PT 8 hours, 41 minutes, and 4.832 seconds. So at this point you may think, great, these durations and periods, but what can I do with this? And that would actually be a very valid question. Let's find out in the next video when we're going to have a look at altering dates and times. Local dates, local times, local date times, and zone date times are immutable. This means that the value of the object cannot be altered after the creation of the object. So technically, you cannot alter them, but we can definitely do calculations with them. The result will be a new object with the new values representing the new date and or time. I know it almost sounds like I'm selling it, but it really is my own not sponsored opinion. There are beautiful methods out there for doing calculations with the dates and the times. They're captured by very many plus and minus methods. We use duration and period to add or subtract to or from a date or time. And then we also have the with and with something something methods. These return a copy of the object with the specified attribute altered. Let's move over to IntelliJ and have a look. So let's go ahead and alter some dates. In order to do so, we'll first need some dates. I'm just going to be working with a local date time here. And I'm going to create one again using the now method. And then in here, I want to show you that I can actually go ahead and alter our date time. But if I were to alter my date time, it would actually not be altered. It's just returning a new object with the specified properties that come out of the calculation. So I can go ahead and say LDT1, and then I can, for example, say plus days, and then say 7. So right now, it's the 8th of the month, so it should be the 15th after this. Let me show you. And as you can see in the output, it says 2022, July, and then the 15th, because we added 7 days to ours. Alright, so as you can see, it's 8 to 12 right now. So what would happen if you were to add 8 minutes? Well, actually, exactly what you would expect. It will also just skip and continue with the next day. So I'm going to change this. And as you'll see, it will also alter the day. So this is actually doing a proper calculation. It's not just updating the minutes. So we also have minus methods, and they're very intuitive. They do the exact same thing as the plus, but then the opposite. More interesting for now is to have a look at the with methods. So I can go ahead and create a new local date time, say LDT3, and then in there I can be using LDT1, and this time I can say with and then specify maybe a specific month. So say that date, but then with the 9th month. So if we're going to be printing this now, we'll see the same date, but with September instead of July. And as you can see, it's still the 8th of July right now. So if we just change the month, it's going to change into September. Alright, I also promised you that I would show you where duration and period would come into place here. Well, we can actually also use plus and minus for working with durations. So in here, I can say local date time, and I'm going to call this LDT2A, and I'm going to say LDT1 plus. And then in here, I can just go ahead and create periods of, and then let's just now go ahead and say weeks 1. Import the period. There we go. Next up, let's print this and see what will happen. And as you can see, in the second print statement, we have been adding a week to our local date 1, resulting in the 15th. Well, let me show you how to subtract something. It's very, very similar. But I also want to show you very briefly how we can do something similar with duration. So I'm going to use LDT1 again, and then I'll say minus this time. And now we're going to be creating a duration, and I'm going to do so with off hours, and I'm going to be subtracting 12 hours here. And then let me print this. Actually, it might start to become a bit vague, so let me print this to be a bit more clear like this. There we go. And as you can see, we now also have one with the alter time, where the time is minus 12. So this is how we can easily calculate with local dates local times, local date times, and also zone date times. We can either use the plus and minus methods and then just go for the very specific ones where we'll be simply adding minutes, but we can also go ahead and use the plus and minus one where we can add and subtract period and duration. Alternatively, we can also use the with methods. We can use these to alternate components of the dates. And I know I've said this already a few times, but dates are immutable. So please be aware that if we add to LDT1, so on line 12 we're saying LDT1 plus minutes. This is not altering our LDT1 object at all. This is staying the exact same. The only thing that's being done is that there's a new object returned with the specified value. Next up, we're going to have a look at how we can convert old dates and calendars to objects of our Java time package. So you may think, great that there is this amazing Java 8 new world for working with dates and times. But there is some legacy code that I need to interact with that's out of my control. Not to worry, there's a solution for this. Java util date works with instance beneath the surface, and it actually leads to the following steps for converting a date. We first convert our old date to an instant, and then convert the instant to the local date or local datetime or zone datetime that we want to have. There's actually multiple ways to do this, but I'm just going to be showing you this one. So let's say we have an old date. And let's specify the current year, maybe a few months ago, and choose the 10th of the month. Alright, so let's go ahead and convert this. What are the steps? Well, first we're going to grab our date and we're going to be changing this to an instant. Next, we actually need a zone because our instant has a zone, and we're just going to grab the system default zone here. Alright, then what's next? Well, we actually have a whole bunch of options. We can convert to a local date, a local time, or a local datetime. Let's go for local datetime right now. And then I'm going to be catching this and store it in a variable. And then we can go ahead and print this. And there we go. Remember when I said it was special that we start to count at 1? Well, that was special, so it turns out. It does not look like what we would expect. First of all, the year is weird, and the month is one higher. Well, this last one we have talked about already. Because the month, it's actually starting to count at 0. So 0 is January, 1 is February, and this makes 5 June. So that's correct. But what happened to the year? This is weird, right? Well, it depends a bit on your exact Java implementation, but mine does the following. So when it goes ahead to the constructor of int year, int month, and int date, it's going to call another constructor. And in this constructor on line 244, you can see that it's adding 1900 to the year. So if we want to create 2022, we would actually have to say 122 in there. Well, let's just say it's deprecated for a reason. Let me close this and change this back to 122. And now if I run it again, you can see that it is the year that we would expect. This may have made sense in the 90s, but for now it's super ugly. But not all Java implementations do this though. Converting a calendar is not that much different. Again, we first convert it to an instant, then get the zone ID from the calendar, and convert the instant to the object we need using the zone ID. Let's go ahead and create an old calendar. And then I'm actually going to be using now for this. So I'll just say calendar get instance. This is the current time. And then what I want to do, I actually want to convert this to a local date time. So what am I going to do? Well, I'm first going to grab our calendar. Then I'm going to say again to instant, add zone, grab the zone ID of our current system. Then I'm going to be converting this to a local date time. And again, if I want to have a look at this, I will have to store it. So I'll do so in a local date time LDT2. And then on the next line, I will be printing this. And let's go ahead and have a look at the result. And as you can see, it's printing the current date and time perfectly well. So this is how to convert an old date and an old calendar to the new Java Time API. Right, I have a challenge for you. What are we going to do? Well, we're going to replace the old Java API with the new one. Here you can see an order util in which we have one method, and that method is going to check whether orders are after a certain date or not. At this point, this is what order looks like. It has a string name and a date. And as you can see, there's not a lot going on except for that. There's a nice toString method though. Alright, and then in our main, we are creating a new order. And then we're doing two things. We're first trying to get the orders after a certain date using a date that's 2 years ago. So our newly created date at line 10 should probably be in this order still because it's going to be created after the year 2020. Then next we're going to filter the order. And this time we're going to create a new date again, which is after we have created the new date at line 10. So this one should be empty. Let's run it to verify. Alright, you're up. Go ahead and change this file to be using the new dates. In the next video, I'm going to show you one possible solution. Alright, so here's one possible solution. First of all, I have modified order. I've called it new order, not to get a conflict in my package. And I've changed the date to local date time. I've also changed the getters and setters accordingly. Then, I went ahead and changed my order util. I called it new order util for the same reason. I don't want to have a conflict in my package. Then, what I did, I changed the parameter to a local datetime type. And then, on line 24, I could actually do something that's a bit easier. I didn't need to use the compare to, I could just use the isAfter method. And when it is after the specified date, then I'm going to add it to the new order list. So I've switched it to get rid of the continue. And then if I run it right now, you get the same result. You'll see the not empty one is containing the cola, but the empty one with the date time that's after when I've created my order is not showing anything. It's empty because there's nothing after this date that's being ordered. Base64 is a way of encoding binary code to ASCII. ASCII stands for American Standard Code for Information Interchange, and it's actually just character encoding, meaning that we gave all the letters, punctuation, and other characters a number, so that we can transfer them as numbers. This is a way of preserving special characters while transferring text. This is especially useful to do when doing computer stuff, because all we have are binary numbers, 1 and zeros that is. If you don't know what binary numbers are, go look that up quickly, because you'll need that knowledge. So what is Base64? Base64 is binary to text encoding. With binary, we can preserve the special characters while transferring text. For every 3 characters written, it produces 4 characters output. And I'd like to show you how it does this. First of all, we need to have a look at the Base64 scheme. this is actually nothing but a translation between a number and a letter. So if we see the value m, we replace it with 12. This is used to convert the ASCII. We also need to know the ASCII table, because with ASCII, the letters have a number as well. This is only a part of the ASCII table, and as you can see, the uppercase A is represented as a decimal 65, and the lowercase a is represented as the decimal number 97. Let's walk through the process of encoding the ASCII value by, starting with an uppercase B. First, we need to grab the ASCII table and write the ASCII value beneath every letter. As you can see, uppercase B is 66, Y is 121, and E is 101. Alright, so let's write that beneath our letters. Next, we need to write this number as a binary number using 8 bits, meaning 8 zeros or ones. Also, when we are representing 1, we need to write this with 7 leading zeros. Why? Well, because of the next step. This is where it becomes interesting. We concat the binary numbers, and as you can see, they're all still grouped by 8 bits. But what we do then is that we group them by 6 instead. The next step is to translate these binary numbers to decimal numbers. And now we go ahead and look in our base 64 scheme and replace the number with the associated character. So when we have by in ASCII, it becomes QNLL in base 64. Let me prove this to you by doing this on the command line. Let's go ahead and create a new string. I'm also going to be using by here. And then I'm going to pipe by using base 64, which is the command line utility. And as you can see, it translates to QNLL. I've already mentioned that ASCII is converting 3 characters to 4 characters, but what happens if the string that we want to convert is not a number of 3? Well, it's actually using a sort of filler character here, and that's the equal sign. So let me show this to you. I say by with 2 e's, it's adding 2 equal signs at the end to still make sure that it's a number of 4, because as you can see, we have 8 characters now with the encoded string. So it's 2 times 4 with 2 filler signs, 2 equal signs. In the next video, let's have a look at Java in base 64. Since Java 8, we have gotten a built-in base 64 class in Java. It's located in the Java util base 64. All it contains are static methods for obtaining encoders and decoders for base 64. These objects contain methods for encoding and decoding. Let's have a look at how to use this to encode and decode in IntelliJ. Let's just go ahead and grab a simple encoder. So we're going to be using a string to store the result. So I'm going to use the base 64 from Java util, and then I'm going to say get encoder. And as you can see, we have multiple options. We also have the URL encoder. But I'm just going to grab the basic encoder here. And I'm going to say encode, and then you can see I have a few options here. If I use the regular encode, it's going to create a byte array, but I'm going to use encode to string. And then I'm going to insert by here as a source, but I need to convert this to a byte array first. And then I'm going to print the result. And as you can see, we get the exact same result, which makes sense because base 64 is the very same process in Java or using the command line utility. We could actually encode before using Java already as well, but then it wasn't built into the language yet, but we had to use an external tool for this. So you may wonder, can we also decode? Yes, and definitely we can also decode. Let's go ahead use the command line to decode something using base64, and then we're going to use Java to decode it. So we're going to be encoding hi there. This is the result, and I'm going to copy it. Alright, so I've copied it. Let's store this in a string called encoded hi there. So here we have the encoded hi there. Let's now go ahead and decode this. I'm going to grab the base64 from JavaUtil again. I'm going to say get decoder this time, and then I'm going to say decode. As you can see, I cannot say decode this string. The result is going to be a byte array. So, well, let's first just go ahead and do decode on our encoded hi there. Now we need to convert our byte array to a string. There's actually multiple ways to do this, but the easiest one would be just to say new string. So I'm going to say string decoded value or decoded hi there. And then I'm going to say new string and insert our byte array as a value. And then I'm going to be printing our decoded hi there. I could also have done this in 2 steps, but I chose to do it in 1. And as you can see, it says hi there right now. So we managed to decode the encoded hi there.
Here we have a little challenge. As you can see, we have a method toBase64 on line 11, but this is using an external library. In the main, we are calling this static method to encode by using base64. The challenge is to rewrite this using JavaUtil base64.
Right, so let's have a look at the solution. We are importing JavaUtil base64, and in the method on line 13, we're using this base64 to get the encoder and encode the string data. This is how to convert from an external library to the JavaUtil base64. In Java 8, some things have been added to interfaces. Interfaces used to only contain abstract methods and constants. Well, there are some additions now. Amongst the additions is the feature that interfaces can contain static methods with a body, so implemented methods. These methods can only be called on the interface, so not on the instance as you can actually do for the static methods and classes. If you want to call a static method on an interface, you use the name of the interface, dot, and then the name of the method. They really belong to the interface and cannot be overridden or hidden in the class. They're simply not accessible without the interface there. That might be a bit counterintuitive, but the good news is that there are some reasons why we would want this. First of all, it allows for implementation in interfaces, and it avoids cluttering of the codebase with utility classes if there is an interface in which it makes sense. My personal, yet professional opinion is that overusing static method in interfaces is definitely a code smell. But let's first have a look at how this is working. So we're having an interface foldable here, and it contains a static method. Please mind that methods in interfaces are public implicitly, so even if I were to add public, it doesn't change anything. Actually, you can see that IntelliJ is making this gray, because it is redundant. It is public, also if I don't specify it. So this is clearly a silly static method. It's just printing something to the console. Carefully fold the object. And then we have 2 classes, an item and a bag. The item implements foldable, and in its main, we are using this foldable.printFold instructions to print the fold instructions. But if we don't implement the class, we can access this as well. So if I'm going to be running this, it doesn't do any different than when I am implementing the foldable class here. So static methods on the interface really do belong to the interface. Let me show you something that could have been on the interface. So we're having all these collections JavaUtil classes. And all of the methods in here could actually also have been on the interface. So this is actually a spot for the collections, but also for the arrays, where it would have been nice if static methods on the interface were allowed, because then we would not need this utility class. But in most other cases, if you don't use it to avoid creating a new util class, it's probably a code smell. It's definitely a code smell for the one that I've been doing here. There are actually more ways in which we can give interfaces implemented methods. Let's explore default methods in the next video. I already spilled the beans in the last video. Default methods allow for implemented non-static methods in interfaces. This means that the method can have a body. So, arguably, you could say that the keyword default is used a bit too much in Java. You could even say it's the default choice for a keyword. So first of all, we have the default methods in interfaces now. Then, default is also used in switches. It's used to describe the situation that we don't specify an access modifier. So we don't use the keyword, but we just leave it out and then call the access modifier default. And we can declare default values for annotations with the default keyword. So, well, poor choice, but it won't ever go away, so you might as well get used to it. Backward compatibility is there for the greater good, and this is actually also why there is now the option to add default methods to the interface. This actually won't break existing code. If you need to add something to the interface after you've made it, you'd have to change all the classes that have implemented the interface. That might sound not too bad, but if you're a third-party library, everyone who's implementing your interface needs to update their code. With the default methods, we can give interfaces a method later without breaking all the classes that are implementing our interface. Quite nicely done, right? And if classes need their own version, they can simply override it. Let's have a look at how this is working. I have two classes that implement foldable, the item and the bag. So I'm going to go over here, and now I'm going to be adding a default method. So I do so using a default keyword, and this one's also not going to return anything, and the method is going to be fold. And I can just print something in here, it's a bit silly, but just to show you that this is not breaking anything. Folding the object like this. And now this didn't break anything. So even though in item I could override it, I don't need to. So whenever I create a new item, like this, I could after this say item fold, and there's an implementation ready. And it will actually fold the item for me. See, it says folding the object. So maybe I want to have something that's more specific. So maybe my item has a private string name, and there were getters and setters in place for it. And actually a constructor that takes up the name as well. And in our fold method, I actually want to specify the name of what I'm folding. So I would go ahead and just say public void fold, and then override it. And that's all. So in here, I could now say folding followed by the name of what I'm folding. Clearly, in here, I would have to specify the name. So this item, in this case, let's go for jeans. So I'm going to be running this, and as you'll see, it says now folding jeans. Whereas if I disable this method, nothing breaks. It will just say folding the object. So what if I would not have added the default method, but I would just have specified a method void fold? This would actually have broken my code a bit, because I would have to implement it at item and I would have to implement it at bag. And this is only two classes, it's not too bad, but you can imagine the impact of this on a larger scale. So let's go for the default choice here and have a default method available. It can be overridden in the class if it needs to be more specific. But let's complicate things a bit more. I'm going to be adding an interface, washable. And maybe in my interface washable, I would also have a default void fold method. And here I would just say something like folding washed object, like this. Right now I'm going to give our item also a washable implementation and do the same for bag. So also here I'm going to be specifying washable. What's going on right now? Well, let's ask IntelliJ. It says bag inherits unrelated defaults for fold and then specifies the types from foldable and washable. So what do we need to do to solve this? We have to override it because now there are two methods with the same name available, and that's a problem. So I would have to go ahead and override it here. So I'll say this, folding bag, and then in here I'll simply enable this one again, and it's overwritten as well. And now it's compiling again. So please mind with these default methods that you choose a specific enough name. This could actually avoid clashes. And if clashes do happen, just know that you need to override it to get rid of the ambiguity. Functional interfaces are a special type of interface, namely an interface with just one abstract method. This means that they can contain many non-abstract methods, such as default and static methods. It actually also means that they can have abstract methods that will be always implemented. This is the case for method signatures from the Java object class, for example, toString. Whether we implement it or not, it is always implemented because every object inherits from the Java object directly or indirectly. At this point, you may wonder what is so special about having only one abstract method. And that would be a great thing to wonder. Abstract methods are a must-have for functional programming. This is because since there is only one abstract method, these interfaces can be implemented in special short ways, known as lambdas and method references, which we'll see later. Let's first have a look at some functional interfaces and the add functional interface annotation in IntelliJ. So let's have a look at the interface that we've already made. Is washable a functional interface? Well, it's not. And if we want to ask this, we can also ask IntelliJ. So we can add the annotation here, add functional interface. And as you'll see, it gets red underlined because there is not just one abstract method, because there are 0 abstract methods. So let's just go ahead and add an abstract method now. So we're going to go for void wash. And as you'll see, our red lines underneath functional interface are gone away, but we have two new related problems. And these are because we never implemented wash. So item and bag now need to have the wash method implemented because they are implementing washable. So let's just go ahead and give them a basic implementation. There we go. And let's do something similar for our bag. And just say washing bag. Okay, error's gone. That's great. So are problems. So what would happen if I were to add something else here? So let's say I'm just going to add a second wash. Wash special. As you can see, the functional interface is breaking now and we have two new problems. The two new problems are because we do not implement wash special. I'm going to ignore these for now. The functional interface problem is because wash special is the second abstract method, and that is a problem. So I'm going to be removing this. It's a great practice to add functional interface, because this way no one else will come around and break your functional interface. We'll see in a bit how important it can be to only have one abstract method in your interface. Just one last thing I'd like to show you, and that is that you can have the method signatures from the object class. For example, if I say string to string like this, it's still a functional interface. It's not breaking. But I can remove this as well, because you can see that IntelliJ highlights this with yellow, meaning it's being implemented, because it's coming from the object class by default. So, alright, let's just remove this, but just know that this can be done. It's a very silly thing to do. Do not do it, but don't be tricked. So, functional interfaces are so important for Java that they actually have a lot of them built in. Let's go ahead and have a look at this in the next video. So we've seen how to create functional interfaces. There's something I need to tell you now. The most common functional interfaces that you'll find yourself needing are already built in. So interfaces with one abstract method provided by Java out of the box. Java offers great options for functional programming with the Stream API that we'll see later. And these built-in functional interfaces play a key role in there. Not only is this great for Java's own APIs, it's actually a great advantage for having uniformity. Because by having built-in functional interfaces, third-party libraries will use this as well. And that helps to easily implement these, because we don't have to go through lots of documentation since we understand how these built-in functional interfaces are working. These functional interfaces are typically implemented with Lambda expressions that we'll see after this video. But let's first have a look at the most common functional interfaces. So here you see a little table, and we have a predicate. And a predicate has one abstract method in it. It returns a boolean, its name is test, and it takes a generic t. Then we have the supplier, which is returning a certain t, and the name is get, which makes sense, right? Because you can use the supplier to get something. Then we have the consumer, which does pretty much the opposite. It doesn't give anything back. It's a void, but it does accept something of type t, the generic. Then we have function. A function has two generics, t and r. R is for the return type. So it's returning this type, and the method is called apply since it's changing something, and it's taking up a t. Let's move over to IntelliJ and see how we could implement these without using Lambda expressions. So let's go ahead and implement a predicate. So we're going to say that our predicate in this case is taking up a string. And we're just going to be calling it predicate. But what I want to do now, I actually want to implement it anonymously. So I'm going to say new predicate, and now I have to override the function in here. So in this case, I'm just going to say that return s and then starts with m, meaning it will return true if it starts with an m and it will return false if it doesn't. But you may see the weird red line on line 12. Why is this? Well, we're actually having one line statement here. Line 7 to 12 is just one statement, so we need the semicolon over here to actually finish our one line statement. So that's one way to do it. The other way to do it without using lambdas would be to be implementing it on the class and then having to override the test. Please mind, this is not how you'd normally be doing this. So if I want to use this one, I could go ahead and say predicate.test, and let's test it for my name, which does start with an M. And let's also start it for another name. Let's test it for Layla, and now run the program. So we need to get the first one to be true and the second one to be false. And as you can see, it's working. So what we have here is called an anonymous implementation. And this means that the implementation right here doesn't have a name. We can only use it on the predicate variable, the local variable that we created here. So first we're going to be doing a challenge and a solution, but after that you're ready for the next step. implementing functional interfaces with Lambda expressions.
Alright, I have a challenge for you. So, what do we have here? We have 4 files. The first file I'm going to show you is the main. And this main is actually containing 2 instances, the transform camel case and the transform screaming snake case. We call the methods to transform the text on both of these instances. And you can see the output below. So on the instance transform camel case, we call the transform screaming snake case. And on the transform screaming snake case, we call the transform text camel case. And it seems to work. What is up? Well, the clue is in our words transformable interface. It contains 2 abstract methods. And both the transform camel case and the transform screaming snake case, they implement this interface, meaning they'd have to override both methods. And in this case, both methods are overridden in the very same way. And then the challenge for you is to see whether you can actually come up with something that's more efficient than organizing your code in this way.
Alright, so let's have a look at my solution. There are clearly more than one options available, but can you see what I did there? So this time I'm calling the transform text camel case and the transform screaming snake case text on the words transformable interface, meaning I have implemented both as static methods. And in this case that made sense to me because, well, we needed them in both methods and actually we didn't really need instances in order to do this. It's more like a utility. So for now these classes are actually empty, but they are implementing the words transformable. Another good option would have been if you would have removed all of this in here and just had one abstract method, transform text for example. And then in both of these, you would only override it with the one that was matching the class name, because that seems to make a lot more sense. Alright, so that was the challenge for this chapter. Let's move on with another challenge, Lambda expressions. Before we start, I would like to encourage you a bit by telling you how horribly difficult I thought Lambda expressions were when I first encountered them. I thought they were so confusing, and the word lambda was also a bit intimidating because it gave me physics vibes and I really struggled with that at university. But here's the good news. After some time working with lambda expressions, they truly become a second nature. Before you get there, we need to go over the basics first. The syntax of lambda expressions is used to implement a functional interface. A functional interface is an interface with only one abstract method, right? So there's only one that needs to be implemented. To be more precise, what we are describing with the syntax is implementing the method of the functional interface. It happens to know what functional interface by context, namely the type that we are talking about or are requiring at that place. Here's a little example. It helps if you read it like this. X and y becomes, the arrow, x plus y. The x and y on the left-hand side of the arrow represent the input parameters of the method. They don't have a type specified. It is allowed to do that, but it's not necessary. The type can be deducted from the method signature that we're implementing. Hence, it can be left out. The right-hand side represents the body. When there are no curly brackets around the body, it represents what the body is returning. So, this implementation returns the result of x plus y. Let's have a look at this example in IntelliJ. So let's start by looking at this functional interface. I can actually add functional interface on top, but I don't need to. It was a functional interface already because it's only containing one abstract method. And this abstract method is calc. It's returning a double and it takes two doubles as arguments. So how to implement this using a lambda expression? Well, here's the most basic one. So I'm saying on line 5, calculator, the type, calling it calculator, equals a comma b becomes a plus b. So what this does is that first of all, it knows I'm talking about the calculator interface because that's the type I'm specifying. Calculator only has one method, calc. So it knows that on the right hand side, a plus b, that's where the body of calc is going. And this body needs to return a double. The input parameters are two doubles, so the a and b on the left hand side must be these two input parameters. Hence, they're doubles, hence we can add them together. So we are allowed to specify the type. But if you do that, you need to do it for both of them. So I can say double A and double B become A plus B. I can actually also add in the return keyword, but not without anything extra. I will have to include an actual method body around that. And mind, if I put a method body around this, I do need to put a semicolon here. So this is actually the exact same line. So let me just go ahead and write it again in the previous way. So simply a comma b becomes arrow a plus b. And then we have the calculator 2, which is the longer version, but it's doing the exact same thing here. There's actually a lot more to say about the input parameters. Let's go ahead and have a look at the input parameters of lambda expressions in the next video. Let's talk a bit more about the parameters of the lambda expression. Clearly, the parameters match the ones of the abstract method in the functional interface that we are implementing. So let's see some examples for 0 or 1 parameters. Alright, so if there are no parameters, you'll always need to have the parentheses in place. There won't be anything between them, but you do need them. If there's one parameter, you actually have a few options. The first one is just to have the parameter. No type, no parentheses. But you are allowed to put the parentheses around them. And you can even specify the type. But if you do so, you must have the parentheses around them. It's no longer optional then. As we have seen already, lambdas can also specify multiple parameters. They're just comma separated in a list. Here are some examples for multiple parameters. The first one might look very familiar. We have the parentheses, that's obligated when you have more than one parameter. And we specify them comma separated. But we can also specify the types. If we specify it for one, we have to specify it for all. And then we can also use var. This is actually not in Java 8 yet, but covering parameters of lambda expressions, I do feel the need to include it. So this is not a Java 8 feature, but if you do know var, as soon as you say var for one of the parameters, you have to do so for all. So you cannot say var x double y, for example. If it's var x, it is going to be var y as well. Let's see some of these in action in IntelliJ. We have two extra functional interfaces over here. We have the creator functional interface with method create, which is returning an object, but it's not taking any parameters. Let's go ahead and see how to implement this. So in here, we would have to go say creator, and then let's just call it creator for now. And then we have to specify no input parameters, so just the parentheses. And then we need to specify the body. So if you remember correctly, it was returning an object, so we can pretty much do anything. So for example, we can always make it return hello there. So whenever we want to go ahead now and say creator.create, because this is the method that we have been creating here. So even maybe just more clear if I call it something else, the creator, for example, then on this instance, I can call the method create. because I have implemented it on line 8. And then if I run this, it's just going to be printing hello there. And I can give it all sorts of bodies, but we'll see more on bodies later. Let's now first have a look at tester. So tester is yet another functional interface. It's returning a boolean and it's taking a string. So let's have a look at how to implement this. So first we go ahead, say tester. Let's call it tTester. And then it takes a string. So we can either just say s, for example, then the arrow, and maybe we want to return a string if it has a length bigger than, well, let's go for bigger than 5. So I called it s over here, the variable, and that is actually not because it's called s in tester. This is a coincidence. There's only one input parameter, so it knows what I would want. So if I call this str, it will work just the same. So it's just going to put the str as the parameter for the test method. And it's going to be returning a boolean. So let's see what happens if I try to make it return something else. So there we go. I say string, and then maybe I just want to say back hi. And as you can see, it does not accept this because hi is not a boolean. It says bad return type in lambda expression. String cannot be converted to boolean. Alright, so how to call this tester? Well, in a very similar fashion. So we're going to call the instance tTester, and then the method is called test, and then we're going to be sending in some sort of value. So for example, we can send in my name here, Micah, which has 6 letters, so this should return true. And there we go, it's printing true. If I were to put parentheses around this, it would still work. And if I would specify the type over here, it would still work as well. This is not necessary though, and it's more common to see it like this without the type, or even without the parentheses if there's only one input parameter. Alright, we have seen the parameter side of the lambda quite well now. Let's focus on the right hand side, the implementations, the body. Let's talk about different bodies. And I don't mean body positivity and all that, though that's very important. Of course, I'm talking about lambda bodies, they're very important too. So far, we've only seen bodies that were one single statement. If a body is one single statement, it can be returning something or nothing. If the single statement results in a void, then that's fine. It's just not returning anything. If it's not void, then that is what is being returned. We can surround these single statements with curly brackets, we have seen this already. But then we must also use a semicolon inside. And if we are returning something, we need the return keyword too. So just to make sure that you understand what I'm saying here. So for example, on line 11, if I'm going to add the braces here, then I need to specify the return statement, and I need to end this statement with a semicolon. And now it's actually a valid statement. It's a bit longer than necessary, but it's valid. We can also have bigger bodies of more than one statement. If we want that, the curly brackets return the keyword, and of course, the semicolons inside the code block are mandatory. Multiple statements can either return something or nothing, just like regular method blocks. Let's go ahead and see that in action. So we're going to be creating yet another tester, tester2, and this one is going to be inserting a string again, but now we're specifying a bigger code block. So what we're doing in here, well, we can actually be using different variables, but for now I'm just going to make it a bit more complicated. So I'm just going to say string as equals, and then I'll just go ahead and grab a substring starting at 0 and continuing till the string length minus 2. And then in here I can do something else. I could, for example, say if as.length equals the string.length, then go ahead and return true. Else, go ahead and return false. And now we have created a lambda expression with a body that consists of multiple lines. It's not a very useful body, but it's consisting of multiple lines. In the next video, we're going to have a look at how we can use lambda expressions for method input in our coding. Lambdas are used in functional programming a lot. You may wonder why or how exactly, but we can use a lambda expression as input for a method. And this actually gives us the power to inject dynamic functionality in the method. Because if you remember correctly, lambda expressions are just a special way of anonymously implementing functional interfaces. So, if a method requires a parameter of a specific functional interface, a lambda expression can be sent in as an argument. I can imagine this all sounds a bit fake, but let's just see this in action in IntelliJ. So let's just go ahead and create a special method here. And this method is going to be public static boolean, and as an input it's going to take the tester interface. So I'm just going to say something like run tester. And then we have a tester t in here, and we can actually run the implementation with t.test. In order to be able to test t, we need to specify a string, and I want to send this in dynamically as well. So it's going to be the second argument of our run tester. Our tester needs to return the result, and then this static method is done. Alright, so we can call this a few times. So for example, the first time I can call it with a very basic implementation. I could say something like the string that we're inserting as an argument, and if the length is bigger than 5, then it should return true. As a second argument, I need to specify the string, so I'm going to insert Micah. And then I'm actually going to wrap this in a print statement, else I cannot see what's happening. So I'm going to do this very same thing again. I'm going to say run test, but this time I'm going to be doing something differently. So now I'm going to say string, and then instead of doing the length, I'm just going to say if it starts with a p, then just go ahead and return true, and our input string is going to be Julianne. So there we go. I could do a few more, but I think the point is clear. What we're doing here, I can show you when we run it. We are calling the run tester method, and this run tester is taking a t which is of type interface tester. And we are implementing this interface anonymously on the fly on line 5 and 6 inside the run tester's arguments lists. Then, in the run tester method, we can actually call the method test on t. Because it's of type tester, we know for sure it has an implemented test. And this is a very, very important basic principle that's going to be used a lot when you get to functional programming and the Streams API. It's important to end this section on lambda expressions with some important remarks about scope and lambda expressions. Unlike methods, lambdas don't have their own scope, but share the scope of the enclosing environment. So we cannot use names for identifiers in lambdas that already exist in the enclosing context, since we cannot have two identifiers with the same name in the same scope. We wouldn't know which one we would be talking about. Because the lambda shares the scope with the enclosing context, we can access fields and methods of this scope inside our lambda, since it's, well, the same scope. Get it? Same scope. Sorry all, I might be repeating this a bit too much. But there's one thing that's surprising here. we can only access local variables of the enclosing scope if they are final or effectively final. This is because the compiler cannot make sense of the lambda if that's not the case. Let me demonstrate these rules in IntelliJ. In order to do so, we're going to be using this functional interface, the calculator, with the method calc in there, returning a double, taking two doubles. Alright, so in this main method, I'm going to be implementing this calculator. So I can go ahead, say calculator C equals, and now I cannot say C, for example, because C has just been specified. So this will not work. Because, well, C is already in this scope. It also says so. Variable C is already defined in scope. So let's go ahead and call this calculator. And let me show you what will happen if I add a C on top here. Again, we get the very same problem. It's going to tell us variable C is already defined in the scope. So let's just go ahead and call this A and B. And now something surprising is happening. The C is no longer read on the right hand side of the expression, because the C at this point is just referring to the integer specified on line 5. So there we say it equals 5. So right now our calculator is turning A and B into C plus A, C being 5. But if you remember what I just mentioned, I said that local variables had to be final or effectively final. Final is done with the final keyword, so this would mean if there were final in front of this. Well, clearly that's not the case, so then it must be effectively final. And that means that final could be in front of there and it would still compile. Meaning we did not set it at another place. So for example, if we try to override 6 here, clearly we can, but then we can no longer use this C in our lambda expression. Alright, that's definitely enough about the basics of lambda expressions. Let's see if you can solve the challenges. Alright, let's have a look at the challenge. We have two functional interfaces, an interface actionable containing a void run abstract method, and a string mappable interface containing a map string method that's returning a string and accepting a string as an input parameter. Alright, in our lambda example, we're doing the following things. So, first of all, if you look at line 14 to 19 and line 21 to 26, you see that we are implementing actionable and string mappable. We're doing so by creating a special class. Now, as a challenge, I want you to get rid of the special class and just implement the interface as a lambda expression using the implementation that's provided here. Then, as a second challenge, you can see on line 9 that we have a private static void print hello world mapped. And it's accepting a string mappable interface. And the string mappable interface is now sent in as a new instance of string to uppercase, since it implements string mappable. What I would like you to do is to rewrite that to sending in a lambda expression again. Alright, and that's it for the challenge. Good luck! Let's have a look at the possible solution. So nothing changed in the functional interfaces, so we can ignore them. But a lot has changed. First of all, the classes below the public class lambda example are gone. They are being replaced by two lambdas. The first one is on line 6, and the second one is on line 7, and I've actually wrapped it in the print hello world mapped call. And this is doing exactly that. So we're using the run action to run the actionable. What we could also have done is created a separate actionable, for example, like this, actionable, and then we could have put this bit in there, and then run our actionable like this. And then the second one was very much needed to actually wrap it inside a method call, because here we are sending the input parameter in as well, but here we want to do it directly. So we specify the print hello world mapped as the method that we want to call, and then we just insert the implementation as a lambda expression of the string mappable. Alright, that's it. It's time for the next very much exciting topic that will take our functional programming skills to the next level. See you there. One of the most important introductions in Java 8 are streams. It enables functional programming in Java. Don't confuse these with the streams we already had, such as input stream and output streams. Oracle defines streams as a sequence of elements supporting sequential and parallel aggregate operations, as you can see here. And that does definitely cover it. But it might sound more complex than it actually is. So let's see if we can explain it without using fancy words and with the use of examples. First of all, we are talking about the sequence of elements. We can easily turn arrays and collections into streams. There are more ways to create streams, but for now, let's just think of an array or collection. When we want to modify or remove specific elements of an array, we could do so using a loop. And if we also want to keep the original, we'd have to make a copy. Say we have an array of names, and we want to have a list of names starting with an A. Then something like this would do the trick. So I'm going to go ahead and loop over the array. And whenever the name starts with an A, or lowercase a, also fine, then I'm going to be adding it to our list. And if I then want to see it after the loop, I would have to print it. I can run this and it will only show the names starting with an A. In this case, only one. We could also concatenate students to all the elements of the array using a loop, except if the name is Micah. That would look something like this. I'll go ahead and create a loop and make sure that my index doesn't go higher than the length of the array. And then I'm going to say if the name does not equal Micah, then go ahead and concatenate students. And then I'll make sure to print it here, else I would have to create a new print statement since there is no override for array. Alright, so let me run this. And you'll see that it has concatenated student to everyone except for Micah. Let's say that now we're working with some sort of list. We would have to make a copy if we want to remove certain items, else we would get the concurrent modification exception. So say we're going to create a list here, and it's going to be a list of strings again, and it's going to be our new names list. Then I'll just say new array list, and then insert the arrays as list, and I'll insert our names array here. Now I'm going to loop over this using a for each loop. So I'll say for every string name in the new names list, and I'll say something silly. If the name equals Micah, then go ahead and remove it from the list. So if I run this, we actually get an exception. We get the concurrent modification exception. You can see it here. This is because we're looping over the list. And when we're looping over the list, we cannot modify it. And this is for good reasons. But we can think of many situations in which we would. Well, there's a bunch of options available, but we can do so with a very elegant syntax of functional programming as well. So working with these loops and these arrays is working perfectly fine, but the syntax is not very elegant. It's hard to read, and maintenance could be hard as well because of that. It's easy to make mistakes, especially if we're going to make it more complex and perform multiple steps on the elements of the array or list. This is where the Stream API is of great value. With the Stream API, we can use a whole new coding paradigm relatively easily, functional programming. So streams allow operations on these sequences of elements. These operations can be done sequentially, but also parallel if the order of the operations doesn't matter. In order to work with streams, we need to create the stream pipeline. The stream pipeline consists of a minimal of 2 operations, but could contain a lot more operations. The first operation we need is an operation to create the stream, also called the source. The last operation we need is an operation to terminate the stream. After this operation, we don't have a stream anymore, but we do have the end result. In between the source and the terminal operation, we can do a lot of intermediate operations. These are optional. For example, operations to filter the stream or modify elements on the stream before calling the terminal operation on the stream. We can have a source operation and 1,000 intermediate operations, but without the one terminal operation, they will never be executed. This is because the stream is lazily evaluated. If there is no terminal operation, nothing will happen. There's simply no need for it. That's quite smart in terms of performance. Some other important things to note, and these are things that you're very likely to encounter as a beginner working with streams. Once a stream has ended with a terminal operation, you cannot work with it anymore. Clearly, you can work with the end result, but you can no longer work with the stream. I can imagine that by now you really want to know how to work with streams. So that's exactly what we're going to be doing in the next video. Let's create some streams. There are different ways to create streams. I've mentioned some already in the previous video, using existing arrays and collections. Creating a stream using an array or collection doesn't modify the original array or collection. We're going to be discussing other ways to create a stream as well. First, I'm going to show you how to create a stream using an array. Next, I'm going to show you how to create a stream based on a collection. Then, we're going to use the much more exciting generate method to create a stream. And finally, we'll use the iterate method to create a stream. Alright, so on line 10, I have created an array of names. And on line 11, I have created the list using the array of names. So, how to create a stream based on an array? Well, it's actually quite easy. We'll just use the arrays util class and then say stream. And in here, we can insert the array. And there we have it. Now we have a stream. And the stream actually has the generic type that the array also has. So in this case, it's string. And we'll call it array stream. And of course, you will need to import stream. It's in the Java util package. So I'll import the stream class from Java util stream for this. Okay, so I can also create one based on a collection. And I happen to have a collection on line 12 of type list. So again, I'm going to be creating a stream of strings, and I'm going to call this list stream. And how to do this? Well, this is actually really easy. I could just go ahead and use the collection and then say dot stream. And now I'm having a stream. Please mind, I've already mentioned this, but this does not modify the original array or list. So What I can also do, I can also create a stream using the generate method. So I can say stream.generate, and then in here I can specify a supplier, and I'll do so using a lambda expression. If you remember correctly, you know that the supplier doesn't take any arguments but does return an object. And in this case, I actually want to go ahead and create a stream that consists of fives, only fives. And I'm going to be storing this in a stream of type integer, and I'll call this generate stream for now. And the last one I want to show you is the stream.iterate. Again, I'm going to be creating a stream of integers here. Call it iterate stream, and then I'll say stream.iterate. And now I have to specify a starting point, and I'll start at 1. And I have to specify a unary operator. This is also a built-in functional interface. And what it does, it takes an argument of a certain type and returns the exact same type. So in this case, I'm just going to say x becomes x plus 2. In this case, meaning that our stream is going to contain all the odd numbers, so 1, 3, 5, etc., adding 2 every time. So you may have noticed it, but if you didn't quite understand the topic of lambda expressions and built-in functional interfaces yet, you'll run into trouble here. So I would recommend you to make sure that you get it down first. When you experience issues understanding the way I was using lambda expressions in the iterate and generate method, that's an indication that it's a good time to revise this topic first. So the examples that we have seen are not an exhaustive list, but these 4 are more than enough to get started with streams. Let's have a closer look at the options for terminal operations to AND or streams in the next video. Streams are not executed until a terminal operation is called on them. They are lazy, so to say. These terminal operations are therefore crucial to complete the stream pipeline. Only one terminal operation can be called on the stream. We're going to have a look at the most common terminal operations. These are the ones that are going to be discussed. For each, min, max, count, all match, any match, non-match, collect, and reduce. And for each one, I'm going to show you the signature of the method and a little example in IntelliJ. So let's start with for each. So for each is not returning anything, and it's taking a consumer as an argument. What it does, it actually does what's in the name. For every element in the stream, it's going to perform the specified action. So I want to show you how the for each is working. And to really show how it's working, I'm going to create a small error first. So I'm going to say for each, and then let's say for every name, I want to be printing this name. So, whoops, my whole thing got red. What's going on? Well, the for each is actually returning a void. And now I'm trying to save the void in something of stream string type. That's not going to work. So I have to remove this first bit. This is just going to be performing a certain action. So I'm going to run this, and what this will do, it's going to create on line 15 a stream of my array, and then for every element it's going to print a name. So that's exactly what it's going to be doing. So let me run this. And as you can see, it has printed all the elements. Let's have a look at the min terminal operation. So what this does, it tries to determine the minimum value of the stream. And it can do so with the provided comparator. This specifies how elements need to be sorted, so it can actually determine which one is the minimum. But there's actually a few things special going on with finding the minimum. What about finding the minimum if it's not there? Well, this is why it's actually returning an optional. And there are even situations in which this method will never be done. So, for example, if I would want to find the minimum on a stream based on my array. So I'll go ahead and create a new stream, and now I'll say min. I must specify the comparator. And the comparator is taking in 2 arguments and then specifying how to compare them. So for now, I could, for example, say first and second. And it knows they're of type string, since my array is of strings, so I can actually call string methods on them. So I can use the methods that are available in string, as you can see. But actually, I only need to compare 2, because it has been built in already. So this minimum, I'm not seeing it anywhere now. This minimum is returning an optional string, so let me just go ahead and catch it here. We haven't seen optional yet, but we'll see it soon. For now, just consider it some sort of wrapper in which the string will be stored. So let's just call this result min and import optional. And now I can actually print the minimum. I'm comparing A to B, meaning that it's sorted from A to Z. And this makes the letter starting with the A the minimum. Alright, but we can also try to get the minimum on the generate stream. This is actually an interesting thing to do. So I'm going to be copying this over. And then in here, I'll say min. And this time I'll specify A and B again, but this time they'll be integers. The good news is integer also has a compare to, so I can just call it compare to here. And then I'm going to be storing the result in an optional integer. And let's call this min generate. And now something interesting is going to happen. So let me remind you of what this generate does. It's just generating an infinite stream, if you will, with 5s. So how is it going to determine the minimum? Well, fun fact, it actually won't happen because it just keeps on sending 5s in. So it will never know whether 5 is actually the minimum or not. And it will just keep on sending 5s. Well, how to know the minimum? If you want the minimum, you will actually have to know all the elements, right? Otherwise you don't know for sure if it's the minimum value. So I'm going to stop my program now because it would go on forever. So the max is actually very similar. It finds the maximum element of the stream using the specified comparator. I'm not going to show it, it's literally just that. But what's more interesting is the all match. All match is returning a boolean and it's taking a predicate as an argument. It's only going to return true if all the elements in the stream match the predicate. And again, if this stream won't ever stop, then it cannot return a result. So let's use the all match on our list stream. So in here, I'm going to be saying nameslist.stream. And I'm going to do all match on that the string is not empty. So I have to provide a predicate here. So I'm going to be inserting an argument, name, and it's going to be true if name is not empty. And I'm going to be printing the result, but I'll first store it in a boolean. And there we go. And I'll add all non-empty in front to actually be able to see it in the outputs. And I'm going to run this. And well, clearly they're all non-empty, so this is true. We also have non-match, and it actually does the opposite. So it returns true if no elements of the stream match the specified predicate. Again, I'm not going to show this. It works in a very similar fashion. And also, for infinite streams, it won't ever finish if none of them match. So for example, if you go to the generate 5 and we say if none match 6, then it won't ever know this. But if we say if none match 5, it will know immediately that some match 5, and then it will return the false for Boolean. So non-match could actually run forever, just like all match, it could run forever, but as soon as it encounters something that's not true, then it's done running. But it potentially runs forever. Any match is more interesting. So any match is just going to see if any element in the stream matches. And again, this could also run forever. It depends a bit on the circumstances. If it's an infinite stream and it cannot find a match, it will just continue looking for a match. But as soon as it finds a match, it returns true. And if it's a finite stream, it will return false if none of the elements match. Let me show you. So I'm going to say Boolean all match stream, and then in this case I'm going to say namelist dot stream dot, and then I'll say all match, and I'm going to see if they all match that the name starts with an M. And it will immediately know that this is not the case, so it will return false. There we go. So let me show this to you. And it immediately knows that not all start with an M. And then we actually have a more complex one, collect. Collect is there in different flavors. For example, we can have the collect, which is just taking a collector, or one that specifies a supplier and to buy consumers. So what does this do? Collect reduces the stream into one end result. And this is a mutable reduction, so to say, and that means that the end result can be appended to or modified instead of needing to be replaced every time. Long story short, it's better for performance pretty much, so it doesn't need to create all the objects constantly, but it can be appended to or modified. So let's go ahead and look at an example. This is actually something that you'll find yourself using a lot. So say that I want to go ahead and filter our list and then collect it in a new list. So I'll say I want to have a list of strings, call it list names longer than 5. And then what we're going to do, we're going to say name list stream filter, and then in here I'm going to say if the name dot length is bigger than 5, you can keep it in the list. And then I'm going to do the collect. And in there I'm going to apply the collectors to list collector, which is just going to create a list as an end result. And then let me print this list names longer than 5 so that we can see the results. And as you can see, it only keeps the names longer than 5. In this case, there are 4 of them, all containing 6 letters. And the last one I'd like to show you is reduce. Reduce takes a certain identity and then an accumulator. So pretty much a starting point and a way on how to add to it. Or we can have the alternatives, which takes an identity, then a by function, which is the accumulator, and how to combine them. What it does, it reduces the stream into one end result. But in order to do so, I'm first going to be creating an array of integers that I'm going to be working with. So I'm going to say int array, int equals, and then in there I'm just going to do 1, 2, 3, 4, 5. And then what I'm going to do here is that I'm going to be creating a stream. So I'm going to say arrays.stream or ints. And then on there, I'm going to say reduce. And in this reduce, I'm going to specify 0 as a first argument, meaning that we start at 0. And then what I want to do, I want to be actually adding the values. So as my binary operator, I'll say x and y becomes x plus y. There we go. And we can store this end result. The end result is of type int here, so I can actually store it in an int. So I'll just say int total equals, and then if I'm going to be printing this, we can see the total. And as you can see, it's 15. So it has some all or ints in the int array. After having seen multiple source operations and multiple terminal operations, it's time to have a look at the optional intermediate operations in the stream pipeline. It's going to make things a lot more fun. So this is exactly what we're going to be doing in the next video. We have seen how to create a stream and how to end the stream, but there's a lot that can be done in the middle. As opposed to source and terminal operations, stream can actually have as many intermediate operations as you'd want. We're going to have a look at the intermediate operations. These are the ones that are going to be discussed: filter, map, flat map, peek, limit, skip, distinct, and sorted. So let's start with filter. Filter returns a stream of a generic type, and this is actually the case for all the intermediate operations. After executing the intermediate operation, you're still having a stream on which you can perform the next intermediate operation, meaning that they all must return streams, else they're not intermediate operations, but they would be terminal operations. So this filter method is called filter, and it takes the built-in interface predicate. We use it to return a new stream without the elements that did not match the predicate. Let's go ahead and apply a filter on our name list. So first we need to turn name list into a stream, and then we use the filter method on it. So I could, for example, say I only want the elements that start with an M. After this, the stream would only contain elements starting with an M. But please be aware, without the terminal operation, nothing is happening. So let's go ahead and print this now. So I'm going to run this program, and as you will see, only the names with the M are being printed. Next, we're going to discuss map. Map also returns a stream. It is an intermediate operation. And we have to send in a built-in interface function implementation, if we want to call it. We use map because it returns a new string with all the elements changed using the provided function. So we use it to update the elements in our stream. So let's go ahead and see an example of map. Again, I'm going to use our name list, and I'm going to be creating a stream. And then I'm going to say map here. And what I'm going to do, I'm going to grab every name from the list and concat the word student to it. Then, again, I'm going to be printing all of the elements. Let's run this, and you can see the result. All the elements will be updated and end with student. There we have them. The next function we're going to have a look at is flatmap. Flatmap is also an intermediate operation since it's returning a stream. For flatmap, we need to insert another function. And what flatmap is actually doing, it's returning a stream with the elements, all collections on the stream, as separate elements on the stream. So there are no collection layers anymore. For example, if you were to have an array of arrays, after this would be simply one level deep array. So no multidimensional arrays anymore. All right, let's go ahead and see this in action. So let's say that this time we don't just have one array, but we have an array of arrays. So I'm going to go ahead, create a multidimensional array here. Call it names to D. And then in here, I'm just going to be using names and names. So it's going to have the array in there twice, meaning it's a multidimensional array. The first element is an array and the second element is an array as well. All right, and then what we're going to do, we're going to be using flat map here to actually turn this into one array. So how we're going to do this? Well, it's actually quite easy. So I'm going to go ahead and say here that I want to change this into a one-dimensional array. So I'm going to say string one-dimensional array. Let's just call this names 1D equals, and then I'm going to say here stream of, and in here I'm just going to be inserting our names 2D. And actually the elements of this stream are now two arrays. So this stream is only going to have two elements. But I want to change that. So I'm going to say flat map in here. And I'm going to use flat map to say, well, this array, so let me just call this array. I want to use this and turn this into the stream of array. And then in here, I will then say it's a one-dimensional array of this. For that, we do need the size. And with this size, we can actually go ahead and say new string and then insert size in there. All right, so if I want to print this, I would actually have to do so using a loop, since the array is not being overwritten in a nice way. So let's now just go ahead and say for every string name in our names1 ID, so the newly generated string array, let's just go ahead and print the name, but I want to concat this with 1D array like this, and we'll print the name. All right, let's run this and see what's going to happen. And as you can see, our 1D array right now is containing all the double values because it started off as two arrays, but now it has actually changed it to a one-dimensional array, hence the name flat map. It's taking out the levels in the layers of the collection. Next up is the method peek. Peek is actually used to do something in the middle, and usually this is nothing but just a quick print statement to see what's going on. That's why it's called peek. So it's going to return a stream with all the elements on the stream, and the specified action will be executed for all elements. Technically, we could change elements in here, but this is a very bad practice. So let's see if we can use this for what it's meant to do. So what would happen if we would put a peek in here? So we're going to do a peek before we turn it into an array. And actually this is getting so big right now that I'm going to put all the operations of the intermediate on a new line. And also the terminal one. So on this peek, I'm going to say, go ahead and just print this value. And as you can see now, we did not have to do the loop that we did underneath this, because we can actually replace this with just a simple peek statement. So let me just put peek in front of here so you can really see what's going on. And then I'm actually going to get rid of this block because we do no longer need it now. And there we have it. It's printing all the peaks. So here we can see that it had already turned it into a one-dimensional list because there's no layers here. So being able to use peek actually in this case prevents us to write 3 full lines of code. So that's definitely a win. You'll find yourself using this a lot while debugging streams. The next two that we're talking about are limit and skip. So limit is just using the word limit, it returns a new stream, and we have to send in a long, which is the number that's going to be used for the limit. So it's going to bring down the stream to the specified number of elements. Then we have skip. Skip also takes long as an argument, and it returns a stream with a specified number of elements skipped. So let's see these in practice. So let's go ahead and use our names 1D here. So I'm going to be creating a new stream using the arrays stream, and then I'm sending in the names 1ID. And what I'm then going to do, I'm going to say skip, and then I'll say skip 1 for now. Then I'll do it for each and I'll print the result. And I'll make sure to include the word skip here so you can see what's going on. And then I'm going to run this. So as you can see, the first element of our list is skipped now. So we used to start with Adnan, and now we're starting with Mary. We can also, in a similar way, limit list. So if I were to do this, just copy it over and then I'll change this to limit. And now I'll just say limit 1. And then what you will see is that it's only going to contain one element in the limit stream. And as you can see, it has only taken the first one and skipped all the rest. So a limit is really saying only do this one and then stop, then you're done. So now it only has limit Adnan. Well, then there's one more thing I'd like to show you about this, and that is that you can also combine them. So we can, for example, say skip 3 and then limit to 5. So this list will contain 5 elements, but the first 3 on the list will be skipped. So let me show you. And as you can see, our list contains 5 elements, but the first 3 elements are skipped. So Adnan, Mary, Laila, these 3 are skipped. Then it takes the next 5. And after that, it is done. So with distinct, we get a stream back that only contains unique elements. So if we go ahead and use distinct on our stream with all the double values, you can probably guess what's happening here. So what we're doing here with the distinct is that I'm going to be copying this over. Then I'll simply say distinct, and I'm going to do a count. And let's just go ahead and store the result of this count in a variable because count is returning a long. So I'll just say number of distinct values. And then I'll print it on the next line. And as you can see, it contains 7 unique values. And that makes sense, because there are 7 unique values on the list. There were 14 in total, but they were all double, so you had 7 left. Alright, the last intermediate operation for now, sorted. You can probably guess what this does. It's going to sort the array. But we actually have 2 flavors of this. We can either use the natural order or specify a comparator if we want to have it sorted in a different way. What this does is that it returns the sorted stream, either by natural order or using the specified comparator. So let's see this in action. Clearly, if we have all double values in the list, sorting them will lead to having the double values next to each other, because this is how they're going to be alphabetically sorted. So here I'm just going to say sorted, and then I'm going to be printing them so you can see the result. And there we have it. You can see that all the double values are next to each other, sorted alphabetically from A to Z. So far, all the streams we've seen were sequentially executed. This was not necessary in all cases. Creating a set, for example, with the filters applied, could have been done in any order. In some cases, this is better for the performance. In the next video, we're going to see just this. Parallel streams. Let's have a closer look at streams. In Java, Streams are actually just an extra layer on top of a certain data source. This way, we can so eloquently perform operations on the data, also known as functional programming. The stream operations we have seen so far were executed sequentially, meaning that the elements are executed one by one, and that the element that's processed first will be the first one on the finish line. This makes the outcome very predictive, especially when the order matters. This is great. Instead of using a sequential stream, we can also use a parallel stream. There are two ways to create a parallel stream. We can create a parallel stream using the parallel stream function instead of the stream function, or we can suggest any stream to behave as a parallel stream using the parallel method. Parallel streams use the fork join framework as a concurrent model. This means that at a certain point, different threads pick up the work, and at another point, they wait for all the threads to be done prior to continuing. You can compare this with a group of friends splitting up to do some shoppings. So you split up with your friends, you all have your separate tasks, but you say, we'll get back to this spot. Even though you are back at the spot, you won't continue until all your friends are there. This is what the threads are doing. For example, if you have 5 threads, this doesn't mean that your application is 5 times as fast. It might be faster, but you're still as slow as the slowest thread. Depending on what you try to do exactly, the outcome can be different. Different compared to running the sequential stream, or even different every time you run it. Alright, so let's just go ahead and calculate the total based on a stream containing a few integers. We're first going to do so using a parallel stream. So I'm going to say stream of, and then in here I'm just going to be listing some numbers. 1 to 10. And then what I'm going to do, I'm just going to be reducing this for now to a number. In this case, it's just a total number. It's just a sum that I'm calculating here. And I'm saying, go ahead and use the identity of 1, and x and y becomes x plus y. Alright, so let's print the total after running the stream. And as you can see, it says now the total is 56. And this is the total of 1 to 10 plus the 1 identity. So let's see what happens if we turn this into a parallel stream. So I'm going to be adding dot parallel here, and now we have a parallel stream. Let's see what the outcome is now. And as you can see, when we run this in parallel, the outcome is not 56, but the outcome is 65 instead. This is due to the identity. This now gets counted every time we reduce the stream. If you remember, reduce is actually a way of turning the stream into one number. And we do so by using the identity and then adding the two numbers. What happens now is that we use the identity a lot more because we have the parallel streams in place. And therefore, the outcome is higher. So be aware of the different outcomes that you could have with a parallel stream. So you may wonder, are parallel streams faster? Let's put this to the test using some of our previous examples. So I'm going to be using this string array names and this name list that uses the string array names. And now I'm going to do two things. First of all, I'm going to be using our name list, turn this into a parallel stream, and then I go ahead and filter, and I'm going to filter for names starting with an M. And then I'm just going to do it for each print statement here. Alright, so how to know if this is faster? Well, let's just measure the time it takes. So let's take a parameter to measure the start parallel. There we go. And let's go ahead and do the same thing for the end. All right, and then say parallel took, and then print the amount of milliseconds it took. There we go. And now I'm going to be doing the exact same thing, but this time for a normal stream. So I'm going to be copying this over. And I'll change this to sequential. And also we're going to have a sequential stream, so no parallel stream this time. And say here, sequential took. All right, so let's put this to the test. Are parallel streams faster? And here you can see at this point they took the same time. So let's run it again and see what happens. This time parallel took 3 and sequential took 0. I'll run it again. Again it's even. And if I keep on running this, you'll see that typically it's either even or parallel took longer. Clearly, it's not a lot of difference, we're talking about milliseconds here, but it is striking that it is longer, because you may wonder, but wait, wasn't parallel supposed to be faster? And well, the answer is no, not necessarily. It really depends on the situation that you're in. There's a lot of management costs involved. The work needs to be, first of all, split up, then later merged, the memory needs to be managed, and more. Think of performing a simple task for your job, something you could do in, say, 15 to 30 minutes. In my case, it could be writing an email with my thoughts for an education program. If you'd have to do this in a team, it would most likely take longer than when you'd have to do this by yourself. So, you may wonder, right, so when are parallel streams faster and a good idea to use? Well, generally speaking, the advice is not to use it too soon. When performance really needs to be improved, it can definitely be a good idea. But it's not necessarily a solution, and you need to be careful and measure whether it's actually going to be effective. Indications that it might be effective are first of all when you're dealing with lots of elements. So when you have a stream with a lot of data, it's more likely that parallel streams are going to be more effective. And the same goes for if you have heavy work on the stream. So for every element you want to do heavy computations, chances are that parallel streams are faster. And of course, when you want to work with parallel streams, the order of execution should not be important, else it's not an option to begin with. Alright, it's time for a challenge. Let's go ahead and create some pipelines yourself. In the challenge file, I have created an array of names on line 8 and 9. There's a lot of names in there. Then there are 3 challenges. The first one is to actually fill the name list. This is now done using a for each loop, and I want it to be done using a stream. The result is a list with values that start with an A, lowercase or uppercase. The second challenge is to go ahead and modify all the elements in the array. We want to concatenate student to all the elements except when the name equals Maaike. Then we don't want to concatenate anything. The third challenge uses the list that we created in step 1. We're going to use this list and filter it for Anthony. So if the value is equal to Anthony, we'll remove it. We'll then make sure to have a look at the variable by printing it, and then we store it all in a list. So the result is a new list with only Angelique and Anja in it. Alright, good luck with this challenge. In Java 8, the optional class was added. If we ask Oracle what it is, the answer is a container object which may or may not contain a non-null value. It might be just me, but it sounds a lot like Schrödinger's non-null cat, value. This is really nothing more than a wrapper object that very nicely deals with the case when the value is null. Optional should be used as a return type. This can, for example, be a query to the data layer asking for an object with certain properties, for example, an ID. If no object is found, this would normally be returning null. And then we'd always have to check for null when we want to do something with the returned value. And that really means every time we wanted to do something with it. It was rather easy to forget it at a later place, and then we would get null pointer exceptions due to forgetting to check for null. Therefore, optional is a more elegant solution for this. With optional, we can use specific methods to get or to do something with a return value. And when it's null, we do not get the null pointer exceptions. Also, the optional value forces us to do not forget that we're dealing with an optional here. So no more forgetting that part, and of course, getting less null pointer exceptions in our code. Let's go ahead and have a look at a little example. In this file, I have created a little example. There are two methods to get a user. One starts on line 20. It's called getUserNull because it can use a null every now and then. The return type is of type user. We send in a name, and if no user with this name is found, we return null. The second one is getUserOptional because it returns an optional. We send in a name, and then it returns an optional containing the user that was found. If no user was found, there is a null value in our optional. Alright, so how to use this? In the sendMail method, I'm using both here. So I started off with already doing the example for the getUserNull because this is what we're used to. We use the method to get the user back, and then we check for null before doing something with it. Is this so very different for optional? Well, yes and no. There's a lot of methods available, but before getting the value out, we do need to check whether it's present. So right now, I'm having an optional user, and I cannot use this as such yet. So I want to go ahead and get the user out. I have tons of options, which we'll discuss in a bit, but for now, let's just look at one example. I can say if recipient 1 is present, and then I can go ahead and get the value out like this. I can do the logic here. So in here, I'm now safe to go ahead and get the value out. If I try to do this without the value available, I do get an exception. So there are lots of reasons to handle this with care. We're going to see how we can deal with this in the next two videos. But before we go there, I'd like to make one side note, and I have already mentioned this, but optional should really be used as a return value only and not as an input parameter or field type. This latter can result in problems with serialization, and your database won't love you for it either. Alright, let's next see how we can create and use optionals. Let's start with creating some optionals. We're first going to see how to create an empty optional, and we're then going to create an optional of a non-null value. And finally, an optional of a value which may or may not be null. Alright, let's start with the empty optional. This is actually great for testing purposes. When we create an optional, we have to specify the optional and then the type. So in this case, I'm going to stick with our user example here. And I'm going to call this optional user. And as I already said, at this point, I'm going to be creating an empty optional. And this is done simply like this. So right now, our optional is empty. So if we go ahead and see if there's a value present, the answer will be false. So let me go ahead and print this as the optional user is present. So this will print empty optional false. Well, it is empty actually, but there's no value present. Alright, so let's go ahead and create a non-null value now. So again, I'm going to say optional and I'll give it the type user. And I'll call this optional user 1. And then I'll say optional of. And then in here, we can go ahead and create a new user. Let's give it a name as well. And now if I'm going to do the same and see whether there's a value present, then we'll get the value true because there's a value this time. Let me run this, show it to you. And you can now see it returns true because we have a non-null value in our optional. But there's an important thing here. So if we want to create an optional of some sort of value that's actually null, we do get an exception. So if it's a user and user at this point is null, we'll get the exception. Let's go ahead and inspect our exception. And again, we have a null pointer exception. So be very careful with this of method because you can only create optionals with the of if there's a non-null value in there. So what to do if you want to do this for a null value? Well, it's actually not too hard. We use the of nullable. So I'll go ahead and again, I'll say optional user, and let's say optional user 2. And then I'll say optional of nullable, and then I can specify the null value. And then now if we check whether there's something present, we'll get the value false again. So these are some ways to create an optional, but more often an optional will be returned by, for example, the Stream API. We already saw an example of this in the previous video, where we used the find first method of the Stream API, which is returning an optional containing the type of the stream, in this case an optional user. When we get an optional back from a method that we were calling, we'd want to check whether or not there's a value in there. In order to do this, we can use many methods. We have seen is present already, but there's a lot more options. Let's go ahead and explore them in the next video. Optionals have methods that allow the programmer to deal with the possible null values in a nicer way, but also other functionality that would require an if statement such as validating the returned result can be done on the optional directly using these methods. These are the methods that we'll be discussing: isPresent, or else get, or else throw, filter, and map. If we want to know whether a value was returned, we use the isPresent method. It checks whether a non-null value is in the optional. If there is one, the result is true. If there's none, the result is false. We have seen this already when we were creating optionals. We can call the isPresent on the instance of the optional and it will then return a true or false. As we can see here, it will return false for the empty and the null values, and it will return true for whenever there is a certain non-null value present. Next, we may want to get the value out, but here we have to be careful with what method to use. If we use get, it throws a no such element exception when there is no value present. If you want to do that, you'd have to check with if present first. But if we do that, it looks a lot like the old way of dealing with null. And if we could only use optionals this way, it would not add a lot of value. Luckily, there are more methods with more options in there. What about the or else method, for example? With or else, we either get the value or we can specify the default for when there's no value present. There are no exceptions this time. You can either get the non-null value out or you get the specified default value. We can also use the or else get method for this. This one is very similar, but instead of specifying the value, we specify a supplier that's only being used when the optional is empty. This is slightly better for performance because the supplier will be used for getting the value in case the optional is empty, but it only runs in that case. So there are no unnecessary objects in our application. If you'd want an exception when the value is not present, but not the standard one, or else throw is the way to go. Here we can specify what needs to be executed if there's no element present in the optional. Alright, here we have three optionals. We have one with nothing in there, the empty optional. We have created it on line 7. We have one with a user in there. We have created it on line 10. And we have one with a null value. We have created it on line 14. What I want to show you first is to use get on an optional with a null in there. So let's go ahead and just try to print our user. I'll say null optional and then I'll go for get. And this is going to throw an exception because it's null, so we cannot get it. As you can see, we're getting no such element exception. But we have other options. If we were to do a or else, we could specify the value of what we would want to have if there was no value present. So I could go ahead, create a new user here and call it Micah. We do not get the no such element exception, but we just get the user Mike. Because there was no user present, it used the default value. We could also have said or else throw, and or else throw takes a supplier. We're going to create a supplier for an exception. So in here, I'll just do a null pointer for now. And right now, if I run this, it will throw the exception because our value is null. And you can see our null pointer exception with our message in the back in the output. If we were to call this on an optional that has a value, it won't throw the exception because it would then just get the value of the optional since it's present. Let me prove this to you. I've used the user optional now, which contains the Lisa user. So I'll run it now and you can see it prints Lisa because there is a value present. Then lastly, we also have the or else get, which also takes a supplier, but this supplier must actually go ahead and give back a user. So instead of just directly adding a user, which will always be created, we'll now add new user and then just specify some sort of name. Let's go ahead and specify Marina. And then if I run this now, in this case, it will not be executing this because there is a value present. And to compare and contrast this, if I were to have the new user directly as an argument, it would actually be executed. So this is lazy evaluation, which is better for performance when there's usually a value present. Before getting the element, we can actually do a filter or a map as well. Let's start with the filter. If the element in the optional doesn't match the predicate, it returns an empty optional. With map, we can specify an operation to be applied to the non-null value. If there is no value, it will return an empty optional. Let's start with filter. So we have an optional, user optional, containing a new user Lisa. I'm going to be filtering here, and I only want to get the value of the optional if it matches the filter. So let me also directly print the result. I'll say user optional, because that's where Lisa is in. Then I'll say filter, and I'm going to see if the user starts with an L. So say get name starts with L. And if that's the case, I actually want to go ahead and get the result. If that's not the case, then I do not want to go ahead and get the result. I'll use the or else method here. In case if there's no result, I want to get the user that I specify here. Luke. Alright, so let me run this. And as you can see, we are getting Lisa back because it starts with an L. Now, say I filtered for something else, starts with an X. Then I would still have gotten Luke back. It's not going to filter anymore after the filter step. So it's going to grab a user optional, filter, and then say Alright, if it's empty, then create a new user called look. If it's not empty, then just get the value. In this case, Lisa doesn't start with an X, so it's going to be empty and it has created look. Let's have a little look at a new example. I'm going to create an optional integer. And I'm going to make sure it contains a value. So I'll say optional of, and I'll just put in the value 30. Now, what I want to go and do, I want to use the map here. So I'll say integer optional map, and now I'm going to specify a function. So I'm going to say if the integer. Now I'm going to say grab the integer and just make it twice the value. And then go ahead and get. And I'm saying get here now, which is normally dangerous because you can get the no such element exception. Since I've created it on the line before, it's quite safe to do so. And I'm going to wrap this all in a print line statement so you can actually see the result. And as you can see, we're getting the value 60 out of here. And this is because of the map function. The map is going to change the value first, then it's going to allow us to get it. If there is no value, it will return an empty optional, and this would have led to us getting a no such element exception on the get. The map does not lead to an exception if there is no value present. Alright, it's time for a challenge. We're going to do 5 things in here. First, we're going to create an empty optional of type string. Second, we're going to create an optional containing an integer. Then we're going to work with these optionals. The third exercise is to get the value out of the empty optional or specify a default name. Clearly there is no value, so we need to specify this default name, and that's the one that we'll get then. The fourth part is that we're going to filter the integer optional and only keep odd values. After that, we're going to either get the value or throw your favorite exception. I'm just going to go for runtime exception in my example. Then, 5, we're going to map the integer to be 1 higher and get the value out. Alright, here's the solution. We had to create an empty optional of type string, and we do so with using optional.empty. It is important then to make sure that the type that we specified is optional of type string, else we'd have an optional with no type. Alright, then we had to create an optional containing an integer. We do so using the optional.of and then just specify the integer. But again, we have to make sure we specify the right type as well, so we have to go for optional integer there. Then we had to get the value out of the optional and specify a default name. We do so with the or else, or alternatively, we could also have gone with the or else get. In this case, I went with or else and I specified Percy as the default name. Then things got slightly more complicated. We had to filter the integer optional and only keep the odd values. And then after that, we would either have to get the value or throw a runtime exception. So what we're doing here, we're filtering for I modulus 2 and the result should not be 0, meaning it's an odd number. If after that there was an empty optional left, I went ahead and specified a supplier that's going to throw a new runtime exception. And then finally, we had to map the integer to be 1 higher and then get the value out. We do so with the map method and we specify a function. In this case, I becomes I plus 1. And then we get the value out. Alright, and that's the solution to this challenge. Let's discuss some of the smaller handy changes in Java 8. Starting with the option to use strings in switch statements. Before Java 8, you could only use switch on byte, short, char, int, enum, and now, since Java 8, also on string. It's actually literally just that. Let's go ahead and have a look. Here we see an example of how we can use a string in a switch statement. It's really, instead of having an int, a byte or an enum, just having a string. And we switch over the string and we specify case labels as strings. It's using the equals method to verify whether they are the same. So if they're not the same lowercase, uppercase, they're not the same according to Java and you will not match. If you need that, you might actually want to go ahead and specify that you want to switch over something to lowercase. For example, it would say to lowercase here. It would now also match if the string above would have Java with an uppercase letter. So let me run this and you will see it's going to print I love Java. Arrays can be sorted. Before Java 8, we could do this sequentially using arrays.sort. In Java 7, the fork join pool was introduced, and this gave a whole range of new options, amongst which working with streams parallel, as we have seen already, but also using a parallel sort option for arrays. It's a similar way of using it. Instead of using arrays.sort, we now have to say arrays.parallel-sort. Is this always faster? Well, actually no. This is similar to the parallel execution of streams. Dealing with something parallel gives a lot of overhead in terms of management. The splitting, merging, memory management and more is actually more work, it's overhead. This is only going to be beneficial for larger arrays. Let's put this to the test. Alright, here's a little script I wrote to test this. So I have two arrays. I create them on line 8 and 9. And I'm going to use random to fill them up. So line 12 to 16 is doing just that. I'm going to make sure that both my arrays contain the same values, that we have a fair comparison here. Right now they have a length of 1000. And then after having set them with random int values, we're going to be sorting them. And we're going to sort them both in different ways. So I'm using parallel sort for the first one, the simple array 1. And I'm measuring the time this is taking. I'm using sequential sort on line 25 for the second one, and again I'm measuring the time this is taking. Alright, so let's put this to the test and have a look, shall we? As you can see, they both took 0. This was way too fast, so let's add some more values to our array so that we can actually have some time to measure. So I'm going to be adding 2 zeros to both. And now we have an array of 100,000 items. Let's see what this will do. And as you can see at this point, sequential sorting is a lot faster. So let's add in an extra 0 and see what happens. And again, sequential sorting is much faster. Well, actually, it's still quite a bit faster, but the difference is not 3 times anymore. It's just faster. Now, if I'm going to be adding one more 0 to it, it's going to be a whole different story. At this point, parallel sorting is a lot faster than sequential sorting. It's even more than twice as fast. So this is something to be really mindful of when using the parallel sort. In some cases it's great and it's going to help you a lot, but this is only the case for huge arrays of data, not for these smaller arrays. So whenever you're working with smaller arrays and you don't need to do anything very complex in terms of comparison there, it's typically smarter to be using the regular sort. Another new feature is unsigned integer arithmetic. This is not as self-explanatory as some of the other new features we have seen. Let's start with unsigned. This means that it is a non-negative value, so nothing below 0. An integer is a 32-bit variable, and the normal range is between the half of -2 to the power of 32 and half of +2 to the power of 32 minus 1. This minus 1 is necessary because 0 is also an option and is considered a positive option. Therefore is the biggest number. One smaller than the negative number is small. With this feature, we cannot magically make integers unsigned. The range of integers then changes from 0 to the positive half. Integers are signed though, and you cannot declare or make them anything else. But we did get some methods on the integer class that works with the int as if it were unsigned. So it's just handling the integers without considering the sign. Let's have a look at an example. Alright, so here we see some examples. And this may work slightly different than what you would think it's doing. So, for example, on line 9, we have the divide unsigned. And this divide unsigned is actually going to give back an integer result, so it's not going to divide it as a double. Then we have the compare unsigned, which is a rather weird implementation actually, because what it does is going to grab each number and then add the minimum value of integer to it and compare these. It will give 0 when they're equal, it will give -1 if the first one is smaller and 1 if the first one is bigger. In this case, we are comparing -6 and 5. Well, unsigned, 6 is bigger, so the result is going to be 1. And then we have the remainder unsigned, which is doing exactly what you think it's doing. It's giving the remainder, considering both input variables unsigned. So you may wonder, why is there nothing for add or for subtract or for multiply in place? Well, this is because this would be the same as normal bitwise operations, so there's an option to do that already. Alright, let's run this and see the results. And as you can see, the integer result of dividing 5 by 6 is 0. The compare gives back a 1 because -6 is bigger than 5 if we compare them unsigned. And the remainder is 1 because, well, if we have 6 and we divide it by 5, we have a remainder of 1. In Java 7, the fork join pool was introduced. In Java 8, some improvements on this and other elements of the concurrent API were introduced. These improvements include new interfaces in the concurrent API, new methods in the fork join pool, there are some additions to the concurrent hash map, and there are new options for working with atomic variables. Also, there's a new class called stamped log. This is a log with several options for controlling read-write access. Here are the Oracle notes for the enhancements on the concurrent API. As you can see, these are very technical details, and demonstrating them will require extensive knowledge of the concurrency framework. Therefore, I've chosen just to show you what is new, and in the concurrency course, you'll definitely come across anything you need to work with the concurrent API, including the new Java 8 features. Java memory is split up in several parts. The stack and the heap are rather well known. The stack holds all the local variables and references for the methods. The heap holds all the objects. The heap consists of different parts, amongst which the perm generation, also called permgen. So the permgen is a part of the heap space. Permgen, part of the heap, is where Java keeps all the loaded classes in their metadata. All static contents such as variables and methods are also kept in the permgen, and so is data about the bytecode. The permgen was famous for its out-of-memory errors, not something to be really proud of clearly, but the reason for this was the poor garbage collection possibilities of the class loaders that were no longer needed. If you hear about the permgen for the first time, it was short but sweet, because in Java 8 the permgen got removed. You may wonder, but that sounded like some space we really needed though. Well, not to worry, this information is now stored in a new space, the metaspace. The metaspace's allocation and deallocation are optimized, aiming for avoiding out-of-memory errors. One of the fun facts about it though is that if you don't set a maximum value for the metaspace, it could grow indefinitely by default. This change actually has a lot of impact on how Java 8 should be managed and how applications are maintained, but when you're programming Java, you don't notice this. Right, so it's time for another challenge. This challenge consists of 3 assignments, and since the topics of this part were non-related, so are these assignments. The first assignment is to create a switch statement for setting an int to a value based on the text input. So if the text input is 1, the integer should be set to the number 1. The second challenge is to create an array of strings with fruits and sort this using parallel sort. Clearly, this is not going to be better for the performance or you're going to be typing a lot of fruits there, but we just want you to make sure that you know how to use parallel sort. And the last assignment is to use unsigned integer arithmetic to find the remainder of -9 and 2. Alright, let's have a look at the solution. On line 13 to 26, we're having a switch statement that is switching over a number, but this number is of type string and its value is 2. We are setting the int number and r that we declared and initialized on line 11. We're having 3 cases, 1, 2 and 3, but we also have the default case specialized. And this is how we can use the switch statement with a string. The second assignment was to create a fruits. I do so on line 29. Then, I'm using parallel sort on line 30 with arrays.parallel_sort, and I'm inserting my fruits array. To make sure that it has been sorted, I'm printing the fruits with index 0, which should be grapefruit, and it is. Then, the third assignment was to use the unsigned integer arithmetic. And we do so by saying integer dot, and we need the remainder unsigned method here. We then specify -9 and 2 and print the result. The result is 1. As mentioned in the beginning of this course, Java 8 is out since 2014. Newer versions of Java have continued to grow. As of this recording, Java 11 and Java 17 are very popular as well. There are some big and popular developments that are not part of Java 8. Clearly, this is an ever-growing list, and this video might very well be outdated. And also, I'm not mentioning all the details here, but just to make sure you know that you cannot use at least the following features in Java 8. You cannot use modules, private methods and interfaces, records, enhanced switched and case statements, simple web server, text blocks, and a lot more.